Now we are going to discuss about linear programming models, graphical and computer methods. What is the use of this chapter? In this chapter, we are going to study about what is linear programming, what are the assumptions that are behind it, what are the properties that has to be met to use linear programming, and how do you solve problems using linear programming. In the case of linear programming, you can solve things using different methods. We'll discuss those methods, and we'll also discuss about some issues which are related to linear programming. So let's start with the introduction of linear programming. Linear programming is a popularly used approach. It is used in mathematical modeling technique. It's not about programming, it's about modeling and solving a problem mathematically. There are 4 important properties in linear programming. These are requirements if you want to use linear programming. In the case of linear programming, we have what is called as objective function. An objective function is used to maximize or minimize something. So when you want to maximize or minimize something, we have some constraints. So constraints are restrictions. To solve these problems, there are different ways of solving it. There are alternative ways, alternative course of actions that could be followed. And the equations in the linear programming are linear and they are with inequalities. So if you talk about linear, they are not square like x square, y square, x power 3, x power 4, square root. These things are not allowed. Plus xy, let's say for example 3xy, appearance of more than one element, one variable together. Okay, this is not allowed in the case of linear programming. So properties of linear programs, it has an objective function, it can have more than one or more constraints, it has alternative courses of action, and if you talk about the objective function as well as the constraint, they are both linear in nature and they are proportional, meaning if suppose I take to do a job 3 hours, if I am given 3 jobs, I should take 9 hours. So it is proportional. And it also supports additivity. Like for example, if I want to add 2 things, okay, if I have 2 items and if I join them, the sum should be equal to sum of individual items. And by certainty, here certainty meaning you know clearly these are the objectives, these are the constraints, and the constraints and the objective does not change during the process of study. Okay, and then you can have divisibility. There can be solutions which can be in fractions, and all the variables that are involved are non-negative variables. So how to formulate linear programming problems? So step 1, you need to understand the problem clearly. Step 2, from there you have to know what is objective and what are the constraints. Step 3, you got to design or define the decision variables. And then from the decision variables, you will express the objective function and the constraints using mathematical notations. So in the case of in the case of linear programming, you will find it's normally a product mix problem. You will have 2 or more products and there will be some resources available and you want to produce these products or you want to maximize the profit of making these products. Let's take an example. Flair furniture company, he is producing chairs and tables. This company is producing chair table, and to do chairs and table they need to do some carpentry and painting and varnishing job. So for a table to be made, they need 4 hours of carpentry and 2 hours of painting and varnishing. For a chair to be made, they need 3 hours of carpentry and 1 hour of painting and varnishing. Total number of carpentry hours available is 240. Total number of painting and varnishing together available is 100 hours. And if you make a table, they will get a profit of $70. If they make a chair, they'll get a profit of $50. So the above things are represented in the table here. You can see there is carpentry, painting and varnishing. And for one table you need 4 hours of carpentry and 2 hours of painting and varnishing and 3 hours of carpentry for chair and so on. Total available hours for carpentry is 240, varnishing you have 100 hours, and profit by selling a table is 70, by selling a chair is $50. So we want to maximize the profit, right? The constraints are simple. It says that you can have only carpentry 240 hours and painting and varnishing 100 hours. So what are the decision variables? How many tables I can make per week and how many chairs I can make per week. So I can write it as T and C. So maximize the profit, 70 into T. Why 70? Because for each table I get $70 as a profit. Similar, for each chair I get $50 as a profit. 70T plus 50C. And then I need to develop, this is my objective function. And if I want to develop my constraints for the carpentry, the total time is 240 hours. So it is less than 240. That's the maximum I can attain. So it's less than or equal to 4 times table, because for every table I need 4 hours. For every chair I need 3 hours. So 4 into T plus 3 into C is less than or equal to 240. Similarly, we want to do for painting and varnishing. Maximum time allowed is 100. So it's less than or equal to 2 times T into 1 plus C is less than or equal to 100. So this means for every table I need 2 hours of painting and varnishing. So clearly we have now the profit, I mean the objective function 70T plus 50C, and we have the constraints. One more important constraint we need to add is always the decision variables are non-negative in nature. So T and C greater than or equal to 0. So that is the first step. You have made your linear problem, linear programming problem. Now we want to solve it. If you want to solve it, you can solve it graphically, but this is possible only if you have 2 decision variables. If you have more than 2, it will be difficult to do so, right? And you also have to understand, because we have non-negative constraints, all the representation will be in the first quadrant of the graph, which is the northeast part of the graph. So this is the representation here. So how to solve it? Step number 1, to solve, we can take the constraint. 4T plus 3C is less than or equal to 240. Just make it equal to 240. And then you assign, let's say, T equal to 0, you get C equal to 240 by 3. Similarly, you put C equal to 0, you get T equal to 240 by 4. So you get these values now. So you put T equal to 0, get C equal to 80, and then put C equal to 0, no chairs, T equal to 60. So you can represent them, T as 0, C as 80. You can represent them like this. So T is 0, C is 80 is here. Number of chairs on the y-axis, number of tables on the x-axis. And then you can put T equal to 0, C equal to 80. And similarly, C equal to 0, T equal to 60. If you use the number of tables here, number of chairs here, doesn't matter. Okay, X and Y can be swapped, no problem. So now the point is this constraint says less than or equal to. So anything on the line and below the line is a feasible region. Anything above will violate the constraint. So if you try, for example, T equal to 70 and C equal to 40, then you will violate. If you put in the constraint, you will violate. For example, 4 into 70 plus 3 into 40 is 400, which is greater than 240. Remember, it should be less than or equal to 240. If you take a point on the line, for example, 30, 40 here, this will be equal to the maximum value allowed. So this is how we represent. Take the next equation, 2T plus 1C equal to 100, represent that one also. And also note what is the feasible region. Because it is less than or equal to, you say the line and the below or the feasible region. Now we have what? 2 representations, 2 lines now. So you can represent both of them in a graph. So this is your carpentry constraint, this is your painting and varnishing constraint. Remember, we need to satisfy both the constraints. So that means this is the area that is a feasible region. Because this part is, it satisfies the painting varnishing, but it does not satisfy the carpentry. Similar, this area satisfies the carpentry, but not painting and varnishing. So this is not included, this is not included. So this is the feasible region, which satisfies both the constraints like. So anything outside the region is called infeasible region, anything inside is a feasible one. So now if you take values and try, if let's say you take 30, 20, you apply to both the constraints, you see both are satisfied. If you take 70, 40, both are not satisfied, you can try 55. One of them, carpentry constraint, is satisfied, but the painting constraint is not satisfied. So simply both of the constraints should be satisfied. This is the deal. Now how to find the optimal solution? There are many ways of finding optimal solutions. One of them is called isoprofit line. Okay, this is a very fast going approach. What you do is this: you take a small possible profit from to the objective function, okay, and you get the line. So here is the case. Let's assume our profit is 2100 in this case. So maximize the objective function 70t plus 50c equal to 2100. This is some value you have to choose from our understanding of this this problem. Okay. Now solve the intersects, draw a graph for it. So how do? You put t equal to 0 and then get c value, c equal to 0, get the t value, put the line. So this is a line for that representation. 70t plus 50c equal to 2100. Okay. And is this the best solution? No, no. So what you can do is you can increase the value, you can increase the profit and keep going. Okay. So like this, you can go next step, next step, next step. But most importantly, the lines you are drawing on the graph should follow the same slope. Okay, they should be they should be parallel to the first line you draw. Okay, you should keep going until a point. If you reach, for example, this one 4200, this line is totally outside our feasible region. So this is not something which we will accept. So if you go one bit sometime down, little bit down, 4100, you will see that line exactly touches one of the points of our feasible region. So here if you want to solve it, you can solve like this: 4100 equal to 70C plus 50C. Take the second equation from the constraint, 2t plus 1c equal to 100, and you solve like you solve equations. Okay, multiply the second line by 50 minus 1, you get the value of t, and you can also get the value of c from that. So this is t is 30, c is 40. That is the maximum point you can reach, because that is the highest point in your feasible region. This is one way. This process is called isoprofit line solution method. A second approach is called corner point solution method. This could be used also. What you do is, the condition is this: every corner point of the feasible region gives you some value. Okay, so it is said that the optimal solution lies at one of the corner points or the extreme points. So like this, in this case you have one corner point, second one, third one, fourth one. Okay, so you know this point, this is 0, 80, this is 50, 0, this is 0, 0, easy. What about this point? Actually this point is an intersect of both the constraints, right? So you can solve the equation for both of them, equate to both of them, or solve them, and you get the value. Solving simultaneous equations, it's very simple. So this is the value 30, 40. So if you apply these values 0, 0, 50, 0, 0, 80 and 30, 40, all the 4 points into our objective function, you get the value. The one that gives you highest profit is called as the optimal solution. So simply there are two ways: isoprofit, where we started with a line, then we continued increasing the line with the same slope, trying to find the region which gives you the maximum profit. And corner point, you take all the points, for each point you find out what is the objective function, what is the profit the objective function gives you. Simple. Next is about slack and surplus. Slack is the amount of resource that is not used. For example, you have some resources. In the case of our constraint, carpentry constraint, we have 240 hours. In the 240 hours, if you don't use the full resource, then the leftover is called as slack. So if you, let's say we are producing 20 table and 25 chairs, 4t plus 3c less than or equal to 240. That was the equation, if you remember. So 4 into 20 plus 3 into 25 is 155. But the maximum possible time available for carpentry is 240. So 240 minus 155 is 85. So slack is 85. So slack is the amount of resource that is not used. Alright, so if you are looking for an optimal solution, the slack should be 0. Okay, you should have used all the time available. Then that is called as surplus. Remember, slack is applicable only for less than or equal to constraint. If you talk about surplus, it is used with greater than or equal to. Okay, so let's say we have a constraint like this: t plus c is greater than or equal to 72. Let's say we have one. Okay, in that scenario, if t is 20, c is 25, and if you add them, it becomes greater than 42, which is allowed because it's greater than or equal to. So the value which you get, the actual amount minus the minimum that is allowed, is equal to surplus. So 45 minus 42, the minimum value given here, is equal to 3. So that means there is a surplus here. See, there are two types of constraints. One is called binding constraint. A binding constraint is where you have an optimal solution where there is 0 slack and 0 surplus. There is no surplus, no slack. And there is what is called non-binding constraint. Here you have an optimal solution, but the optimal solution has either positive slack or positive surplus. Okay, so these are the few things you got to know. So let's talk about how to solve these problems. Normally people use many softwares, many tools to do this job. Okay, and we are not going to discuss any tools, so I'm going to skip the slides which are with the tools here. Right, we can use many tools to solve this kind of LP problems. So let's go further. The next step you are going to see in this topic. So you can see we can use many tools. Then we want to solving minimization problem. Until now we have seen how to solve maximization problem. Okay, we want to maximize the profit. Sometimes we want to minimize things like. So if you want to find out minimization, that can be also be solved graphically. Right, here we can use the same corner point method. And we can use, instead of using iso profit, we use iso cost line. Okay, So ISO cost line is used for minimization problem, ISO profit is used for maximization problems like. So here again we need to find what is a decision variable that will yield the minimum cost. Okay, here is an example. They have a holiday meal turkey ranch. Here they are buying two brands of food for turkey feed and blending them to produce some diet for the turkeys they are rearing. So there are two brands, brand 1 and brand 2. For each brand there are 3 types of ingredients and the composition is given here, and the minimum month requirement of each ingredient is also given, and the cost per pound of each brand is also, the feed is also given. So how to decide? Now you can see the number of pounds of feed you want to purchase. Okay, so you can put like x1 and x2, and then if you want to, what you want to minimize is the cost. So 2 times x1 plus 3 times x2. Okay, that is in cents. Okay, and then what will be the constraint like? You can see here 5x1 plus 10x2. Okay, and then 5x1 plus 10x2 is greater than or equal to 90. Why greater than or equal to 90? Because this is minimum monthly requirement. Okay, that's a minimum. Similar, 4x1 plus 3x2 is greater than or equal to 48, and so on. So you can write all of them. Don't forget our non-negativity constraint. So for every variable you have, decision variable, you will say they are non-negative. Okay. So you can see here, you can also convert, like for example, if you want to write 0.5 x1 is greater than or equal to 1.5 ounces, you can multiply both sides, or you can just bring this one here, you can say x1 is greater than or equal to 3, just to make our calculations easier. Then you want to represent them in a graph, so you can just start to put values here, like you can put here like x1 is 0, get x2 is equal to 90 by 10, and then which will be x2 equal to 9, and then you can put x2 is equal to 0, and you can divide x1 equal to 90 by 5, and you can draw the lines. So here is it. They have drawn the lines for ingredients A, B, and C, right? And you will see wherever they match, wherever they all meet each other, then you get the feasible region. Please note here, this is all greater than or equal to. So it should be line above the line, okay? So for A, it will be all these places, here, 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 like this. For B, like this line means it's above here. C, it is this side. So this is the area where all of the constraints match. So now if you want to find the solution, how to find? You can take each value, like for example, you can take A, B, C and find out. These are the corner points. How to get A? This is intersection of the C constraint and the B constraint. So take them, equate them, solve the equations, get the values. So that is what is being done here. And then take all these A, B and C, apply the values for x1 and x2 from the A, B and C points into the objective function and see which one gives you the minimum one. Remember, we are minimizing here, we are not doing maximization, and we can find out the answer. You can also solve this using ISO cost line, as you know. Right, in the case of ISO cost line, here we will move towards the lower left region. Okay, so we will start from here and then we push down. Instead of pushing up in the case of profit, ISO profit, here we'll push down until we reach a point where it will touch one of the edges, and that will be the minimum most value you can get, matching or meeting all the constraints. So this could also be solved using some tools which they have discussed. There are some special cases in LP, linear programming. There are 4 mainly special cases. Number 1 is called no feasible solution. 2 is unboundedness. 3 is redundancy. 4 alternate optimal solutions. What do you mean by no feasible solution? Okay, no feasible solution means you will not have a solution that matches or that satisfies all the constraints. Okay, this is sometimes possible. So let's say you have a constraint like this. If I want to put it in a graph, this is how it is. So these 2 constraints meet here, this constraint is here. So there is no common region where all the 3 constraints meet. Because remember, this is x1 greater than or equal to 7, should be here. All others are less than, so they won't meet. So this is no feasible. Then we have what is called unboundedness. Okay, so let's say we have an unboundedness problem and you are asking the person to find out the maximization. Because the solution is unbound, it has no limits, it's an open bounded feasible region, you won't be able to get an answer for it as well. So here is an example. So let's say we have the feasible region like this for these constraints here. So this is a feasible region. If you ask me for maximization, I can go all the way, there is no end here. So I won't be able to give a solution. This is called unboundedness solution. Next one, redundancy. you might have more than one constraint, some constraints which are not affecting the solution, which are not affecting the feasible region. Then this is redundancy. This is also common in real world applications. So you can see here you have these constraints. If I'm going to draw them as a graph, you will see this constraint here, x1 less than or equal to 25, it is here. Even if I remove this constraint, the feasible region is not going to change. It will have no impact on the feasible region if I remove or if I keep it. So simply, it's a redundant one. So it has no effect on the feasible region. And sometimes you have linear programming problems where you can have more than one optimal solutions. Okay, you will get more than one answers. So this allows a management or anybody with the flexibility to choose whichever alternate solution is possible. Like for example, if you have the feasible region like this, all this colored here, so anywhere between A and B, from this point to this point, all the points here, any combination, okay, on the line is an optimal solution. You can take anything. Next, we are going to study what is called sensitivity analysis. Sensitivity analysis, until now, we have assumed that things don't change. It's a deterministic assumptions, meaning we are certain about the relationship, we are certain about the objective function and so on, but in real life, things change. So it is possible that the contribution rates of each decision variable, which means the values given in the objective function changes, or maybe the constraint values in the constraint coefficients, which is the left hand side of the constraint changes, or the resources that is available, which is the right hand side of the constraint changes. So these things can be analyzed using what is called sensitivity analysis, which is also called as post-optimality analysis, parametric programming, or optimality analysis. Lots of names for it. So you have to see what will happen. If there is a change, we can go for trial and error method, try changing different values to see what happens, but it's not a better approach. So you want to use something like analytic post-optimality analysis. Okay, we want to tell us, okay, after doing the LP, there is a range of values. If the changes is within the range, it will have no impact on the optimal solution, or it will not do anything on the optimal solution. Here is an example. You have a company which makes quality speakers. We represent it as x1 as a decision variable, and stereo receivers, which is x2. Okay, and this is made with some skilled people. Some are electricians, some are audio technicians, and the equations are given. Let's assume it's given. This is to maximize maximize your profit. So you have drawn all this, and this is your feasible region. From the graph, it's clear. Now, the optimal solution is also clear. A equal to A, which is 0 speakers, 20 receivers, profit will be 2,400. Let's say if you apply this optimal value, x1 is 0 and x2, which is 20, in the constraint, like here. Okay, 2x1 plus 4x2 is less than or equal to 80. You make it equal to 80, you will find it's equal to 80, so there is no slack available. It's a binding constraint. No slack, no surplus, binding constraint. Then if you take the audio technician hours, it's the same, applying the same equation, 3x1 plus 1x2. The value you will apply is x1 is 0, x2 is 20, okay, and it was less than or equal to 60, so 60 minus 20, 40. You have slack here. So this is a non-binding constraint. What do you mean by non-binding constraint here? If we increase the non-binding constraint, if there is some 1 or 2 units increase the non-binding constraint, it will increase the slack. But if you increase the binding constraint, you will get profit. That is the idea here. Okay, so let's start with changes in the objective function coefficient. This is called contribution rates. These are the contribution rates. So if there is a change, okay, if there is a change in there, and you will find the feasible solution will not change, which will remain exactly the same. Only that the slope of the iso profit or the iso cost line changes, okay. And if there is a modest increase in the objective function, might not change the optimal corner point. But if there is a huge increase, then there is something possible, okay. But you want to know how much I can change in the contribution rate that it will not affect my corner point. So here is an example from the same problem. So if let's say increase the profit of stereo from 120 to 150, so the equation becomes 50x plus 150 x2, or you can decrease it to 80, so it will become like this. So if you change each one of them, you can see when I change it, it passes through some other point. The old one is A, and if I change it to this, it still maintains A, okay. So even if it becomes 50x plus 150 x2, the original one is this, it still remains the same, but if I change it to 50x1 plus 80x2, it changes, the value changes. So these things could be solved using many of these tools to get an answer. Right, if you check changes, if you make changes in the technological coefficient, which are in the constraints, the left-hand side of the constraints, okay, so it will impact. If the amount of resources needed to produce a product changes, coefficients in the constraint equation will change. But this will not affect the objective function, okay. This will have a significant change in the slope. It can also change the optimal solution. So here is a simple example where you have this kind of equation. This is the original one. This is your feasible solution, and this is your optimal solution. If you change the coefficient from 3 to x1 to 2x1, no change. Still the optimal solution remains the same as a point. Okay, but if you change this constraint here, instead of 4x2, you change it to 5x2, then the optimal solution value changes. And if you change the right hand side of the constraint, okay, which is called resources, okay, this may lead to different amount of profit, and this might also have impact. So in the case of sensitive analysis, we are going to find answers for this. How much should I be paid? Should be paid for additional resources. Okay, how much resources will be useful? You cannot keep increasing the resource. At one point, that's it. After that, even if you increase the resource, it will have no impact. Okay, so you can see here changing the RHS will change the feasible region unless the constraint is redundant. If it is redundant, it will have no impact. Right? Often it also changes the optimal solution. We have some definition called dual price or dual value. What do you mean by dual price or dual value? Is the amount of change in the objective function that results from a unit change in one of the resource. If you change the resource, one unit change in the resource, how much impact will it have on the objective function? Okay, and dual price for a constraint is the improvement in the objective function value that results from one unit increase in the right hand side of the constraint. So if you increase one unit on the right hand side of the constraint, what will be the increment? And it's a constraint, dual price for a constraint is the improvement in the objective function. Okay, how much will it improve in the objective function? So that is also how much you can increase RHS. If you keep increasing RHS beyond the limit, it will have no impact on the objective function. Okay, it will not increase. It will not increase by the dual price, which is the value by which it is supposed to increase. If you keep increasing, it will just have, it will be like an excess resource. It will be like a slack resource. It will have no impact. Okay, so the dual price is also within some limits. So here is an example from the same old example here. So the constraint representing 60 hours of audio technician, but if you change the constraint to 100 hours, okay, for the electric technician, okay, changed constraint representing 100 hours, then the value changes. With 100 hours, the profit changes. Okay, there's a different value. But if you, for example, if you use a constraint of the electrician to be 60, it is different. Okay, the profit changes also. If instead, if you make it like the electrician to have 240 hours, it will not make anything. It will be like 7,200 with a profit. Anything beyond 240, it will not change. Because it will be like 0.60, that is the point these two constraints meet. After that, if you keep going up, it does not meet. Okay, the optimal solution will not change. That is the idea there. So these things could also be solved using some of these tools. There is what is called shadow price. What do you mean by shadow price? This is the change in the objective function that results from a 1 unit increase in the right hand side of a constraint. Okay, so you increase the right hand side of the constraint, which is the resource, by 1 unit, and that will make some changes in the objective function. That is called shadow price. So we got to watch out, right? If you want to improve the objective function in a maximization problem, and we also look for minimization problem, the objective function's value should decrease. That is an improvement. In the minimization means decrease, in maximization means increase. And this ends this chapter.